Example 3.3. An electric toaster uses nichrome for its heating element. When a negligibly small current passes through it, resistance at room temperature 27 degrees Celsius is found to be 75.3 ohm when the toaster is connected to a 230 volt supply. The current settles after a few seconds to a steady value of 2.68 ampere. What is the steady temperature of the nichrome element? The temperature coefficient of resistance of nichrome averaged over the temperature range involved is 1.7 into 10 raised to minus 4 degree Celsius. Now see here, resistance at 27 degrees Celsius, that is given to you 75.3 ohm. So we can consider 27 degrees Celsius temperature as reference temperature. Now, supply voltage, that is 230 volt, when the steady current, that is 2.68 ampere, we want to find the temperature of the nichrome element. Okay. Now alpha, that is given to you 1.7 into 10 raised to minus 4 degrees Celsius inverse. Here see, at that particular temperature, what is the resistance, that is not given to you. But see, voltage and current are given to you. So we can use the equation resistance at temperature T, that is equal to resistance at temperature T0 into 1 plus alpha T minus T0. This temperature T that we want to find. And at that temperature, what is the resistance, that is not given to you. But at that time, what is voltage and current, that is given to you. So we can write R at any temperature T, that is V by I, that is equal to R at temperature T0 into 1 plus alpha T minus T0. Now substitute the values. Voltage V, that is 230 volt, current I, that is 2.68. Resistance at reference temperature T0, that is 75.3. 1 plus alpha, that is 1.7 into 10 raised to minus 4. Temperature T that we want to find. The reference temperature T0, that is given to you 27. Now, from this one, you can calculate this capital T. Clear to all of you? Next example, 3.4. The resistance of a platinum wire of a platinum resistance thermometer at the ice point is 5 ohm and at steam point is 5.39 ohm. When the thermometer is inserted in a hot bath, the resistance of the platinum wire is 5.795 ohm. Calculate the temperature of that hot bath. Now see here. At 0 degrees Celsius temperature, we can take it as a reference temperature. The resistance is given to you 5 ohm. So that is R0. Now at temperature T1 equal to 100 degrees Celsius, that is the steam point. Resistance R at temperature T1, T1 is 100 degrees Celsius. So we can write R at 100 degrees Celsius, that is 5.39 ohm. Then the temperature of hot bath that we want to find, we don't know. Then at that particular temperature of the hot bath, the resistance R at T2, or we can say R at temperature T, that is 5.795 ohm. Say here alpha is not given to you. So now we can prepare the equations like this. R at any temperature T, that is R0 into 1 plus alpha T minus 0, because here the reference temperature, that is 0. So we can write R0 into 1 plus alpha T. Simplify this one. So RT equal to R0 plus R0 alpha T. Take this R0 on left hand side. So we will get RT minus R0 equal to R0 alpha T. Similarly, prepare another equation for 100 degrees Celsius. So R100 equal to R0 into 1 plus alpha into 100 minus 0. That is equal to R0 into 1 plus 100 alpha. Again, simplify this one. So R100 equal to R0 plus R0 into 100 into alpha. Take this R0 on left hand side. So R100 minus R0 equal to R0 into 100 into alpha. Now take ratio of these two equations. Okay. So RT minus R0 upon R100 minus R0 equal to R0 alpha T upon R0 100 alpha. R0 cancelled. Alpha cancelled. Now take this 100 on other side. Make T as the subject of equation. So T equal to RT minus R0 upon R100 minus R0 into 100. Now substitute the values. R at the temperature of hot bath, that is given to you 5.795. Then resistance at 0 degrees Celsius, that is 5 ohm. Then resistance at 100 degrees Celsius, that is 5.39. Again, R0, 5 into 100 as it is. Now simplify this one. You will get the temperature of hot bath. Clear to all of you? Now next topic, that is electrical energy power. Now see, suppose we consider any conductor, the resistance of which, that is R, and current I is flowing through this resistance R. Now here these two endpoints of the resistor R are denoted as A and B, and the current is flowing through the resistor from A to B. Now we know this thing, current always flow from high potential to low potential. It implies that when current is flowing from A to B, then we can say this thing, the terminal A of the resistor R, that will be at higher potential, and terminal B, that will be at lower potential. Suppose potential at A, that is VA, and potential at B, that is VB, then we can write here VA is greater than VB. So potential difference between A and B, that we can write V equal to VA minus VB. Clear up to this one? Bolo it. Bol it, શું હતું?
સર રેકોર્ડિંગ બંધ હતું, હવે ચાલુ છે.
Now suppose delta Q amount of charge is flowing in time delta T, which constitute this current I, then we can write delta Q, that is I into delta T. Now, when this delta Q amount of charge is at terminal A, where the potential is VA, then we can say the potential energy of charge delta Q at terminal A, that is U at A equal to delta Q into VA. And when this charge delta Q reaches at B, where the potential is VB, its potential energy at point B will be UB equal to delta Q into VB. Therefore, when this charge delta Q is transferred from terminal A to terminal B, change in its potential energy delta U, that is equal to U at B minus U at A, that is equal to delta Q into VB minus VA. But we can write VB minus VA, that is minus V. So delta U equal to minus delta Q into V. Clear up to this one? Now, as per law of conservation of energy, we can write delta K plus delta U, that is equal to 0. So delta K, that is minus delta U. Substitute the value of delta U, that is minus delta Q into V. So this is equal to minus delta Q into V. Therefore, change in kinetic energy, that is delta Q into V. Now, as per work energy theorem, the change in kinetic energy, that is equal to work done. So we can write delta W, that is equal to, now here substitute the value of delta Q I into delta T. So we can write delta W, that is VI delta T. Now if we take this delta T on left hand side, then delta W upon delta T. So this delta W upon delta T, that is called electrical power consumed. In this process, when delta Q amount of charge is transferred from terminal A to terminal B in time interval delta T. So electrical power consumed P, that is equal to V into I. And this electrical power consumed, that is converted into heat. So we can say the electrical power consumed P, that is V into I, itself is the heat produced per unit time. And we can write this equation like this also. If we substitute V equal to IR, then power P, that will be I square R. If we substitute I, that is V by R, then power P, that is V square by R. So we can say this is the electrical power consumed, or we can say the heat produced per unit time in this process. Clear to all of you? Now see, next topic, why the transmission of electricity is carried out at high potential. Say, we know this thing, the electricity is produced in powerhouse, and then from powerhouse, the electrical energy is transmitted to end users through the conducting cables. If we use any cable to transmit the electrical energy from powerhouse to end user, that cable have some resistance. And if some resistance is there, then definitely the power will be, electrical power will be converted into heat, and it will dissipate in the atmosphere, and we can say that is the pure loss of energy, right? So to minimize this loss during the transmission, what we can do? Now see here, the power P, which is equal to V into I, this we want to transmit. Now, if this particular power is transmitted through the cable, which one is with resistance equal to RC, then the power loss in the form of heat, so power loss in cable PC, that is equal to I square RC. But we can write I that is equal to P by V. So here if we substitute I that is P by V, then power loss in the cable PC that is equal to P square RC upon V square. But P and RC that is constant one. So we can write here the power loss in cable proportional to 1 upon V square. So power loss that inversely proportional to the square of potential. And therefore we can say if the transmission is carried out at high potential, then the power loss in the form of heat that can be minimized. Clear to all of you? Now, next topic, that is series connection of resistors. When resistors are connected between two terminals A and B as shown in the figure, then this connection of the resistors, that is called series connection, in which current have only one path to flow from A to B. So in series connection of resistors, the current through each resistor that will be same one. Now suppose here across these two terminal A and B, the potential difference applied that is of V volt. Or in other words, we can say between terminal A and B, the battery having V volt is connected. So across each resistor, the potential difference that will be different one. Here across R1, the potential difference is V1. Across R2, potential difference is V2. Across R3, the potential difference is V3, as shown in the figure. So we can write the resultant potential difference between A and B, that applied voltage V, equal to V1 plus V2 plus V3. Now, as per V equal to IR, we can write V1 that is equal to IR1. Current I is flowing through all these three resistors, and that is same one. For V2, we can write IR2. For V3, we can write IR3. If we take I common, then V that is equal to I into R1 plus R2 plus R3. So take I on left hand side. We can write V by I that is equal to R1 plus R2 plus R3. Now suppose here the equivalent resistance of this combination, that is R. Then we can write V by I that is equal to R, that is R1 plus R2 plus R3. Equivalent resistance of this combination means what? Equivalent resistance means if these three resistors are replaced by any one resistor, and if the same voltage constitute the same current in the circuit, then we can say the total resistance offered by this combination to the circuit and the resistance offered by that single resistance to the circuit, both are same one. This is the meaning of equivalent. Okay. Now, if we have n resistors connected in series, then we can write the equivalent resistance R, that is equal to R1 plus R2 plus R3 up to Rn. Now suppose all the resistors connected in series are with same value. So we can write if R1 that is equal to R2 equal to R3 up to Rn that is equal to R dash. Then the equivalent resistance R that is equal to NR dash. And here always remember this thing. In series connection of the resistors, the equivalent or the resultant resistance that will be greater than the largest one connected in this combination. Clear to all of you? Now next, parallel connection of resistors. Suppose the resistors are connected between two terminals A and B as shown in the figure, such that the current I have different paths to flow from A to B. Then this type of connection, that is the parallel connection of resistors. Here suppose across these two terminals A and B, the potential difference of V volt is applied, or in other words, we can say, suppose between A and B, the battery having V volt is connected, which constitute current I in the circuit. So when this current I reaches to this junction, then it will be divided in three parts. Suppose I1 current is flowing through resistor R1, I2 current is flowing through resistor R2, and I3 current is flowing through resistor R3. And when all these three currents reaches here and comes out from this connection, then again the total current that will be I. And here, see, suppose we think about resistor R1, then one terminal of resistor R1 that is directly connected to A, and the second terminal of R1 that is directly connected to B. In the same manner, R2 and R3 are connected. So the potential difference in parallel connection of resistor across each resistor will be same one, but the current through each one will be different one. Now see here, at this junction, total current I is distributed as I1, I2, I3. So we can write I that is equal to I1 plus I2 plus I3. Now I that is V by R. So as per that we can write current I1 that is equal to V by R1. Current I2 that is V by R2. Current I3 that is V by R3. Take V common from this one and take it on left hand side. So we can write I by V that is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Clear up to this one? Now, suppose the equivalent resistance of this entire connection, that is R, it implies that if this connection of three resistors that is replaced by only one resistor having resistance R, then the same voltage will constitute the same current. Then we can say that resistance R is the equivalent of this combination or connection. So if equivalent resistance is R, then we can write R equal to V by I. So we can write 1 upon R, that is I by V. So in this equation, if we replace I by V by 1 upon R, then we can write the equation 1 upon R equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So using this equation, when we calculate R, then we can say that is the equivalent resistance of this parallel combination of resistors. Suppose we have n resistors in parallel connection. Then the equivalent or the resultant resistance for that, we can write the equation 1 upon R equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 up to 1 upon Rn. Now here, if all the resistors connected in the parallel combination are with same value, means if R1 that is equal to R2 that is equal to Rn that is R dash, then we can write 1 upon R that is equal to 1 upon R dash plus 1 upon R dash plus 1 upon R dash up to n times. So resultantly, we can write 1 upon R that is n times 1 upon R dash. So we can write R that is equal to R dash by n. And always remember this thing, in parallel connection of resistors, the resultant or equivalent resistance that will be smaller than the smallest one connected in the combination. Clear to all of you? Now here one simple example is given to you in which three resistors are connected between two terminal A and C as shown in this figure. And now here, suppose we want to find the resultant current flowing through the circuit I, or we can say we want to calculate the current I constituted by the potential difference of V volt across A and C. Then first of all, we have to calculate the equivalent resistance of this combination. So here see, R2 and R3, these two resistors are parallel. So we can prepare the equivalent circuit like this. Replace these two resistors which are in parallel, R2 and R3, by one resistor which is equivalent to this combination. Suppose that resistor is R23. So we can write R23 that is equal to R2 R3 upon R2 plus R3. So now this particular circuit we can prepare like this. A to B resistor R1 as it is, and B to C, this parallel combination is replaced by one resistor R23. Now you can understand here this resistor R1 and this resistor R23, these two are in series. Suppose the equivalent resistor of this series combination is R, then finally our equivalent circuit, that is A to C, only one resistor R. And this resistor R equal to R1 plus R23. Now substitute the value of R23. So we can write R1 plus R2 R3 upon R2 plus R3. Now current in the circuit I, that is equal to V upon R equivalent. So V by R, that is equal to V by R1 plus R2 R3 upon R2 plus R3. So in this way, we can simplify the circuit. Clear to all of you? The next topic, that is cells, EMF and internal resistance of the cell. Okay. Now the simple device with the help of which we maintain the constant current in the circuit, that is called the battery or cell. Here one electrolytic cell is represented in the figure. In electrolytic cell, two electrodes are there. One electrode that is known as positive electrode, which is denoted by P. Another electrode that is known as negative electrode, which is denoted by N. And these two electrodes are immersed in the electrolytic solution in electrolytic cell. Here, we will not bother about the chemical reactions which takes place in this particular electrolytic cell. But just remember this thing, due to some chemical reactions between these electrodes and electrolytic solution, there will be the exchange of charges between electrolytic solution and electrodes. And due to that, one electrode becomes positively charged and another becomes negatively charged. Clear to all of you? Now, when this particular cell is not connected with any resistor in the outer circuit, at that time, whatever is the potential difference between these two electrodes, that is called EMF, means electromotive force of the cell. See, we discussed this thing, one electrode that is at positive potential because it is positively charged, another one that is at negative potential because it is negatively charged. So, when the current is not flowing through the battery or through the cell, સેલ તમે આવી રીતે આઉટર સર્કિટમાં રેઝિસ્ટર સાથે કનેક્ટ ના કર્યો હોય અને ક્લોઝ લૂપ ફોર્મ ના થતી હોય તો ઓબ્વિયસ છે કે સેલમાંથી કરંટ ફ્લો થતો હોય નહીં. So in that particular case, we can say the potential difference between these two electrodes P and N, that is V plus minus minus V minus. So V plus plus V minus, that is called EMF of the cell. So in short, you have to remember this thing, when the current is not flowing through the cell, at that time, whatever is the potential difference between two terminals of the cell or two electrodes of the cell, that is the EMF of the cell. But if resistance R is connected between these two electrodes in the outer circuit, and if the current I is flowing through this resistor, in that particular case, we can say the same current I that is also flowing through the electrolytic cell also. Now, when the current is flowing through the electrolytic cell, actually the current is constituted due to flow of charges, right? So here in outer circuit, the current is constituted due to flow of electrons. But inside the cell, the current constituted, that is due to flow of ions. And here, the motion of the ions from one electrode to another electrode, that is opposed due to internal resistance of the cell. Suppose here internal resistance of the cell is R. So some energy loss will take place. Now, when the current is flowing through the cell, at that time, if we take the potential difference between these two electrodes, then that will be less than the EMF of the cell. And for that, we can write the equation V equal to E minus IR, where V, that is known as the terminal voltage of the shell. Clear to all of you? Now see, when current I is flowing through resistor R, then as per Ohm's law, we can write V, that is equal to IR. So here in this equation, if we substitute the value of V, that is IR, then IR equal to E minus I into small r. If we take this I into small r on left hand side and take I common, then we can write current I into capital R plus small r, that is equal to E. Therefore, I, that is equal to E upon R plus R. So here, this is the equation of the current constituted in this particular circuit through the resistance R, which one is connected in the outer circuit with the shell having EMF E. Clear to all of you? Example 3.5. A network of resistors is connected to a 16-volt battery with internal resistance of 1 ohm, as shown in figure. A. Compute the equivalent resistance of the network. B. Obtain the current in each resistor. C. Obtain the voltage drop across AB, across BC, and across CD. And now the network is given to you. See, here, first we can say this thing. These four ohm resistors between A and B are connected in parallel. Similarly, 12 ohm and 6 ohm between C and D are also connected in parallel. So, the equivalent resistance between A and B, that will be 4, both are same one, parallel. So, resistance across AB will be 4 by 2, that is 2 ohm. Now resistance across BC, that is simply 1 ohm as it is. Then across C and D, 12 ohm and 6 ohm are parallel. So resistance across CD, that is equal to 12 into 6 upon 12 plus 6, it will come to 4 ohm. Then we can say all these three are in series. So resistance across AD, that is resistance AB plus resistance BC plus resistance CD. So 2 plus 1 plus 4, that is 7 ohm. So this is the resultant resistance between A and D. Clear to all of you up to this one? Now, current supplied by the battery of 16 volt to the network, that is I equal to E upon R plus R. As per that equation, E, that is 16 volt given to you, capital R, that is the equivalent resistance of the network between A and D, and that we calculated 7. And small r, the internal resistance of the battery, that is given to you 1 ohm. So 7 plus 1, 8, 16 by 8, that is 2 ampere. Now current constituted here, that is 2 ampere. Now when this 2 ampere current is divided in two parts between A and B, but see here, both the resistors are identical one. 4 ohm, 4 ohm. So 2 ampere current that will be distributed equally. So 1 ampere that will flow through the upper 4 ohm resistor and 1 ampere current will flow through the lower 4 ohm resistor. Now, when from both the resistor, the current flowing that is 1 ampere, then the potential difference across both 1, that is 4 into 1 as per that, between A and B, the potential difference that will be of 4 volt. Clear to all of you up to this one? Then after, when current reaches at B and comes out from B, again it will be 2 ampere through this 1 ohm resistor, and therefore 2 into 1. So 2 volt potential difference will be there between B and C. Then after, at C, again these 2 ampere that will be distributed in 2 parts. But now see here, between AB, the potential difference is 4 volt. Between BC, it is 2 volt. And when 2 ampere current is flowing through this cell, so here internal resistance of the cell is given to you 1 ohm. So potential drop will be 2 volt. So 4 plus 2 volt, 6 volt plus 2 volt, 8 volt. And total voltage of the battery, that is 16 volt. It implies that 16 minus 8, that much potential drop will be across CD. It implies that across 12 ohm resistor and 6 ohm resistor in parallel combination, the potential difference across each one, that is same one. So here across CD, the potential drop that will be 8 volt. So current through 12 ohm, I, that is V by R. So I1 current through 12 ohm, that is 8 by 12, that is 2/3 ampere. Similarly, we can calculate current through 6 ohm resistor, that is I2 equal to V by R as per that 8 by 6, that is 4 by 3 ampere. Clear to all of you? So now here current through each resistor, potential difference across each resistor, the equivalent resistance of the network, everything is calculated. Say here across CD, the potential drop that is of 8 volt that we calculated here. And therefore, we calculated the current through 12 ohm and 6 ohm. But suppose this potential drop across this combination is not known, but the total current here, that is 2 ampere, means total current is known. Then how this total current will be distributed in both the resistors? So for that, we have the equation I1, that is the current through resistor R1, that is R2 upon R1 plus R2 into total current I. And I2 equal to R1 upon R1 plus R2 into I. The resistor which you say that is R1, through it you have to take current I1. And the resistor which you say that is R2, through that you have to take current I2. So your total current I that will be distributed in both the resistors as per this equation. Note down this equation. Now next topic, that is cells in series and in parallel. Means when more than one cells are connected in the circuit. So if the cells are connected in series and when the cells are connected in parallel, then what will be the equivalent EMF that we have to understand. First, take cells in series. Suppose, as shown in the figure, two cells having EMF E1 and E2 with internal resistances R1 and R2 respectively are connected between two terminals A and C, and the current flowing through this combination, that is I, then this type of connection of the cells, that is series connection of the cells. Okay. Suppose the equivalent EMF of this combination, that is E equivalent, and the equivalent internal resistance offered by these cells to the circuit, that is R equivalent, then we can represent the equivalent circuit as shown in this figure. Now, suppose here we take the terminals A, B, and C as shown in the figure in this connection. Then the potential difference between A and B, VAB, that is equal to VA minus VB, that we can write E1 minus IR1, because here the current I is flowing through the cells. And the potential difference across BC, that we can write VBC equal to VB minus VC, that is equal to E2 minus IR2. So resultant potential difference across AC, that we can write VAC, that is VA minus VC. Now here in this equation, add the potential at BVB and subtract VB. So we can rewrite this equation as VA minus VB plus VB minus VC. This VB cancelled after all this equation. But now VA minus VB, that you can write E1 minus IR1, and VB minus VC, that you can write E2 minus IR2. So VAC, say it is V, then that is equal to E1 minus IR1 plus E2 minus IR2. So we can rewrite this one as V equal to E1 plus E2 minus I into R1 plus R2. So we can compare this one with V equal to E minus IR. So we can write V, that is equal to E equivalent minus I into R equivalent. So here E equivalent, that is equal to E1 plus E2, and R equivalent, that is R1 plus R2. So if n cells are connected in series, then we can write the equivalent EMF of the series combination of the cells, that is E1 plus E2 plus E3 up to En, and R equivalent means the resultant internal resistance offered by this combination to the circuit, that is R1 plus R2 plus R3 up to Rn. Clear up to this one? Now here see, in this series combination, the cells are connected like this: positive, negative, then after positive, negative. So here in this case, we write E1 plus E2 plus E3 plus up to En. But suppose any cell is connected in opposite manner. It implies that for first cell positive, negative, and then after for second one, here negative terminal is there and positive terminal is on this side. So in that particular case, you have to write E1 minus E2 like that. So remember this thing, this E equivalent E1 plus E2 plus E3 up to En, that is the algebraic summation. Clear to all of you? Then after the cells in parallel. Now see, if two cells are connected between terminal A and C as shown in the figure, positive terminal of both the cells that is connected to A through B1 and negative terminal of both the cells that is connected to C here through B2. Then this type of combination of the cells that is known as parallel combination. If equivalent EMF of the combination, that is E equivalent, and the equivalent internal resistance, that is R equivalent, then this is the equivalent circuit. Suppose here the total current constituted, that is I, and through cell E1 having internal resistance R1, the current flowing, that is I1, and through the cell of EMF E2 having internal resistance R2, the current flowing, that is I2. Then here the potential difference between B1 and B2, that we can write VB1 B2, the same one that is across A and C, because between A and B1 as well as between B2 and C, there is no other component. So whatever is the potential difference between B1, B2, the same one is there between A and C. So we can write VB1, B2, that is equal to VAC, and say it is V. Then for first cell having EMF E1 and internal resistance R1, we can write this potential difference V, that is E1 minus IR1. And for second cell, the same potential difference, that we can write E2 minus I2 R2. We know in parallel combination, for each component, the potential difference, that is always same one. Now, here total current I enter to this particular junction, and I1 and I2 are coming out from the junction. So we can write I, that is equal to I1 plus I2. Okay. Now, here we can write from these two equations, one equation, that is I1 R1, that is equal to E1 minus V. Therefore, I1 equal to E1 minus V upon R1, and another equation I2 R2, that is E2 minus V. So I2, that is equal to E2 minus V upon R2. Now substitute these values of I1 and I2 in this equation. So I, that is equal to E1 minus V upon R1 plus E2 minus V upon R2. Therefore, I, that is equal to E1 upon R1 plus E2 upon R2 minus V upon R1 minus V upon R2. So I, that is equal to E1 upon R1 plus E2 upon R2 minus V into 1 upon R1 plus 1 upon R2. Clear up to this one? Now, make this V into 1 upon R1 plus 1 upon R2 as a subject. So take it on left hand side and take this I on right hand side. So V into 1 upon R1 plus 1 upon R2, that is equal to this E1 upon R1 plus E2 upon R2 is directly written as R2 E1 plus R1 E2 upon R1 R2 minus I. Therefore, V into, here again R1 R2 is taken LCM. So R1 plus R2 upon R1 R2, that is equal to R2 E1 plus R1 E2 upon R1 R2. Now take this bracketed term on left hand side, that on right hand side. So V equal to R2 E1 plus R1 E2 upon R1 R2 into, now R1 R2 upon R1 plus R2 minus I into R1 R2 upon R1 plus R2. So this R1 R2 cancelled. So resultantly we can write therefore V, that is equal to R2 E1 plus R1 E2 upon R1 plus R2, this one, minus I into R1 R2 upon R1 plus R2. Now compare this equation with V equal to E equivalent minus I into R equivalent. So we can write E equivalent, that is equal to R2 E1 plus R1 E2 upon R1 plus R2, and R equivalent, that is R1 R2 upon R1 plus R2. Clear to all of you up to this one? Now the equation of current is rewritten here. I equal to E1 upon R1 plus E2 upon R2 minus V into 1 upon R1 plus 1 upon R2. So we can write V into 1 upon R1 plus 1 upon R2, that is equal to E1 upon R1 plus E2 upon R2 minus I. Therefore, we can write V, that is equal to, now without taking LCM, take this bracket on right hand side. So E1 upon R1 plus E2 upon R2 whole thing divided by 1 upon R1 plus 1 upon R2 minus I upon 1 upon R1 plus 1 upon R2. So this one is the equation for two cells connected in the parallel. But suppose n cells are connected in parallel, then we can extend this numerator here for first term like this. V equal to E1 upon R1 plus E2 upon R2 plus up to En upon Rn divided by 1 upon R1 plus 1 upon R2 plus 1 upon R3 up to 1 upon Rn minus I upon 1 upon R1 plus 1 upon R2 up to 1 upon Rn. But we know this thing. When we take cells in parallel, so at that time their internal resistances are also in parallel. And for parallel combination of resistances, we know the equation. This 1 upon R1 plus 1 upon R2 up to 1 upon Rn, that we can say it is 1 upon R equivalent. And this one is also 1 upon R equivalent. Clear? So here, now we can compare the same equation with V equal to E equivalent minus I upon 1 upon R equivalent like this. So for n cells in parallel, the equivalent EMF that will be given by this term E1 upon R1 plus E2 upon R2 up to En upon Rn whole thing divided by 1 upon R equivalent. Clear to all of you? So in general, you can write for n cells in parallel, E equivalent, that is E1 upon R1 plus E2 upon R2 plus up to En upon Rn divided by 1 upon R1 plus 1 upon R2 up to 1 upon Rn. Now, whatever the number of cells are given to you in the parallel combination, you have to write up to that number of steps here. 3 સેલ આપ્યા હોય તો E3 upon R3 અને અહીંયા 1 upon R3 સુધી લખો. 5 સેલ આપ્યા હોય તો E5 upon R5 અને અહીંયા નીચે 1 upon R5 સુધી લખો. And the equivalent resistance, for that you can write the equation 1 upon R equivalent equal to 1 upon R1 plus 1 upon R2 up to 1 upon Rn. This is as per the parallel combination of resistors which we already discussed. Clear?